Good morning to all and welcome to lecture number 7. So today we'll start chapter number 2 in which we will be studying the low-level computer vision. And in this low-level computer vision, we'll talk about basically what is meant by image pre-processing. Then we'll do the review of uh, linear and non-linear filtering, then how 2D convolution is done, and then after that, uh, how basically noise is removed by using the averaging filter and also by using median filtering approach, and then how edges are detected. So that is nothing but the high pass filtering. And then in that edge detection, we'll see the basic operators which are used for edge detection. And after that, we'll study LOZ, that is Laplacian Gaussian, and difference of Gaussian, that is ZODOG. These are the approaches which are used for edge detection. And then after that, we'll be studying the canny edge detection technique, and then scale-space approach for detection of the edges. And then after that, we'll study how to detect the edges in the multispectral images. And at the end of this chapter, we'll be studying different operators which are used for detection of the line, detection of the corner, and so on. So like that way, in this chapter, we'll be studying low-level computer vision processes and so on. So if you look at the computer vision pipeline, so the first step of the computer vision is image acquisition. So image can be captured with the different cameras. You know that in my first lecture I talked about electromagnetic spectrum. So in that electromagnetic spectrum, this one, you have this visible spectrum whose wavelength is ranging from 400 nanometer to 700 nanometer. So generally we capture the visible images and so on, but only it's not like that. Okay, we can capture only the visible images or like that. We can capture the images of this one, X-ray images, which works in the X-ray range. And then this one, we can capture the satellite images, we can capture the thermal images, we can capture the PET images, we can capture the OCT imaging, then fundus images are there, and so on. So there are several cameras are available, like as a simple normal camera, which captures very beautiful picture about the which works in the visible range of electromagnetic spectrum, that is from 400 nanometer to 700 nanometer. Then X-ray camera works in the range of X-ray wavelength. And then so every camera's wavelength is different, and then that it works, but principle remains same, that is light will fall on the object, and then object will reflect that light back, and then light will be recorded. Only thing is that in case of thermal camera, instead of writing with the help of light, in case of thermal camera, temperature is captured of the object, and then temperature is recorded. So that is the only change in thermal camera and other cameras and so on. So images are acquired with the help of different cameras. So that is our first stage. Now when you are capturing the images, that images may contain the unwanted things. Maybe sometime it may happen that you might have seen that when you capture the image in the dark room, you get a very dark image, and then most of the objects are not visible to recognize and so on. So first, what you have to do, basically, we have to improve the quality of that image. Like by using enhancement technique, we can improve the quality of that image, and then image will become good, and then further we can process that image for getting the meaningful information. Similarly, you might have experienced that when you travel in the car, and if you see the beautiful picture, and if you capture the picture of that one, sometimes that image get blurred because of the motion of the car and so on. And then the blurred portion, you don't see the object very clearly. So you can overcome that one by using deblurring algorithm, that is image restoration technique. and then you can make the bad quality image into the good quality image. So that is nothing but that is also a pre-processing. So image enhancement is also pre-processing technique, means we are making the image which will be really good for further processing in the pre-processing state. Similarly, suppose for example image is corrupted with noise, a lot of noise is there, so we'll see what is by noise in the image and so on. And then we have to remove that noise first, and then after that we can extract the features from the image and so on. So this pre-processing step is very, very important. Sometimes we have to detect the edges of the image and so on. So image enhancement technique, image basically restoration technique, or a noise removal technique, or edge detection technique. Or suppose for example sometime it may happen that when you are displaying the image, and if that display is not gamma corrected, then image will not be displayed very correctly, so you have to do the gamma correction. So gamma correction also is a part of pre-processing. Or like for example if your image is distorted or like rotated or scaled or like that, so you have to make sure that this distortion should be overcome. So all those steps comes under the pre-processing. Then this pre-processing is called as the low-level vision or low-level computer vision. And after that, from that clear image, you will get the image which will be really suitable for extracting the good set of features. And those features are used for either detection or segmentation further. So this part is generally we consider that as a mid-level image processing. And then after that mid-level image processing, we can apply the high-level image processing or high-level computer vision basically. And then we can develop the application of this computer vision, which can be used like for detecting anything or predicting anything or analyzing anything or so on. So there are already we have seen in our last lecture, there are several applications. Means I told you in my last lecture that 70% problems of the real world can be solved by using the computer vision. So this is a very powerful subject and so on. So in this chapter, we are going to focus only this part, that is low-level computer vision. Okay, so in this low-level computer vision, this is nothing but the image pre-processing. And as a computer vision engineer, data pre-processing or a data cleansing is a crucial step. And most of the CV engineers, that is computer vision engineers, spend a good amount of time so that your data will be very clear for further processing, like as a mid-level computer vision, and for building the model of high-level computer vision and so on. So this is the building block, basically a basic step which is very highly required in any computer vision application. So some of the examples of this data pre-processing includes, like for example, outlier detection or missing value treatment, or removing the unwanted things, or removing the noise and so on. So these are nothing but the pre-processing steps or low-level computer vision techniques and so on. So image pre-processing is the term for operation on the images at the lowest level of abstraction, right? So this operation do not increase the information. We are not increasing the information or content of the image, but they decrease if entropy is an information measure which is generally used in computer vision or image processing or machine learning application and so on. So generally we try to remove the unwanted things from the images, and that is nothing but the pre-processing. So the aim of pre-processing is an improvement of the image data that suppresses the undesired distortion. We don't want the undesired things because that may create a problem, or that may reduce the quality of the features which will be extracted in the mid-level computer vision and so on. So it may enhance some of the image features relevant for further processing and doing the analysis task and so on. So pre-processing is very, very important stage in the computer vision or low-level image computer vision and so on. So there are 4 types of low-level computer vision techniques or image pre-processing. First one is nothing but the pixel brightness transformation or brightness connection. So that I told you the example of image enhancement means if you take the image in the dark room, then most of the pixels will be at the lower intensity side, and then you may not be able to see the image very clearly. And then further processing or basically detecting that image or finding the meaningful information becomes very, very difficult. Or as I told you that when you have captured the image, when you are traveling in the car or in the vehicle, and then your camera is also in the motion, so basically because of the motion and so on, when you capture the pictures, so sometimes you get the blurred image, so you have to remove that one. So pixel brightness transformation and brightness correction is very, very important. So this is one of the technique. Another technique is the geometric transformation. Geometric transformation, as I told you that this permits or the elimination of geometric distortion that occurs when an image is captured. The normal geometric transformation operations, like as for example, sometimes image is rotated or it is scaled or it is distorted, and so on. So you have to remove all those things by using geometric transformation. So that is also considered as a low-level computer vision. The third and most important part of this low-level computer vision is image filtering. We'll see what is by filter, why it is used, and what kind of different filters are there, and then how does it work, and so on. So basically, the goal of filtering is to modify or enhance the image properties, or to extract the valuable information from the picture, such as you can extract the edges, or you can extract the corners, you can extract the blobs, and so on, or you can remove the noise and so on. So these things can be achieved by using image filtering. So we'll study all those things in detail in our today's lecture also. And the last part of this image pre-processing is that our computer vision, low-level computer vision, is that detection of the edges, detection of the line contour or region of interest, or detection of the corners and so on. So overall, basically, all various low-level vision algorithms are dealing with filtering or denoising or detecting image features like as the edges or contours and so on. And if you detect or do it properly, it will be really useful for further processing of the computer vision, or like as a mid-level computer vision and so on. So I told you that the first thing, that is pixel brightness transformation and brightness correction. So look at this image of this girl, which is taken in the dark room. So most of the pixels are having the intensity at the lower side. So maximum intensity is around 110. So most of the pixel intensities are at up to 110 and so on. So the quality of this image is not that very good. But one of the technique, that is histogram stretching, means if you stretch this histogram to this side, and this will be really useful. Basically, if you stretch this histogram to this side, it will be really useful. Sorry. Okay, so it will be really useful if you stretch these histograms like that way, this way, and then if you display, this is called the histogram stretching. So you are just doing the brightness correction or intensity correction and so on. And if you after stretching this histogram, you get the histogram like this, and then if you visualize image with this histogram, you get this kind of pictures. So this picture is a really good picture as compared to the original picture. So this is nothing but the simple technique of image enhancement, which is also considered as a pre-processing or low-level computer vision and so on. So you got basically by pixel transformation, you got a improved quality of the image. We are not basically removing any kind of things, but we are basically improving the quality of the image in the image enhancement and so on. Then another technique which we are going to see or study in detail about image filtering or image averaging and so on. So if you take the average of the image several times, of the pixel average in spatial domain and so on, you can remove the unwanted things, that is nothing but the noise and so on. So look at this one. So this is your original image, and if you take the average of this image several times, then finally you get the very good image, which is noise removed and so on. So image quality has been improved by simple image averaging and so on. This way we are making the image of good quality, which will be really suitable for further processing. Otherwise, this kind of noise, which unwanted things, will be really making a confusion, or the quality of feature may be decreased and so on. Another thing of this one, I told you about the gamma correction. So generally what happens when you're displaying the image on the computer screen or cathode ray tube, CRT, and so on, you know that in generally in CRT there are three guns. One is argon, then with electronic gun. In electronic gun there are three guns. One is basically this R gun, red gun, then green gun, and blue gun. So this signal which is connected to this gun is transmitted in the form of electrons, and then it strikes to the screen of that CRT. Now when it travels from gun, this electron travels from gun to CRT through various depletion plates, like as a horizontal depletion plate or vertical depletion plate and so on. So this draw, it is expected that it should travel and it should maintain the linearity property and so on. But in actual, it does not maintain the linearity property. See, this is the expected thing. Like voltage and light relationship in the CRT, but actually it happens like this. So there is a non-linear transmission of the electrons from the gun to the this CRT, screen of the cathode tube. So you have to make the correction, this correction. So how to make the correction of this one? So just you have to add some value like this. So if you add this value like this value in this value, then you will get the linear this one. So this adding this value is nothing but the gamma correction. So what happens basically if your image is not gamma corrected and so on? So if your image is not gamma corrected image, and if you are displaying that image on the computer screen, then you can see that this at the lower side, we are not able to distinguish between the different gray levels. We most of the time we see that all those gray levels are same. This is because your image is not gamma corrected image. But after this gamma correction, see, after applying this gamma correction, this relation becomes linear between the voltage and light in case of CRT, and then you can see the image with the gamma corrected correction. So you can see the difference, clear difference between this shade and this gray shade, this gray shade and this gray shade. So all those consecutive gray shades can be we can identify with our human vision system very clearly. So that is the advantage of doing the gamma correction. So gamma correction is also comes under the low level computer vision and so on. Nowadays in most of the hardware, this gamma correction is inbuilt facility, so we don't have to do separately in the images and so on. Most of the hardwares are now came up with the gamma correction and so on. Now I told you that the third and most important part of this low-level computer vision is nothing but the filtering. So what is by filtering basically? So basically, if you might have studied this one in undergraduate also. And basically, the role of filter is to pass certain frequencies and block the other frequencies. Like for example, if you have designed a low pass filter with cutoff frequency equal to fc, so from 0 to fc it will pass the frequency, and above the fc it will block the frequency. So only frequencies from 0 to cutoff frequency will be passed by the low pass filter. In case of high pass filter, from cutoff frequency onward it will pass all those frequency, and below cutoff frequency this filter will block all those frequencies. So that is called as the high pass filter. In case of band pass filter, so there are two cutoff frequencies, fc1 and fc2 is another cutoff frequency. So between fc1 and fc2 this filter will pass the frequency. Below fc1 all those frequencies will be blocked, above fc2 all those frequencies will be passed. So this is called as the band pass filter. And in case of band reject filter or band stop filter, between FC1 and FC2, it is exactly opposite to the band pass filter. So between FC1 and FC2, all those frequencies will be blocked. And then below FC1, all those frequency will be passed. Above FC2, all those frequency will be passed. So this is called as the band stop filter. So particularly in the computer vision, this low pass filter and high pass filters are used, and there are special use of this low pass filter and high pass filter to pass this one. So basically this is done in spatial domain. So you can do in two domain. One is spatial domain and another one you can do it in frequency domain. So spatial domain means that the domain of image which we capture when we capture the image and when you represent that image. So this image is represented in a space. So this space coordinates are x coordinate and y coordinates, and then intersection of x and y coordinate is nothing but as a it is called as the pixel coordinates. So at these pixel coordinates, all those reflected intensities will be recorded, and then this representation of the image is called as the spatial domain representation because it is represented in a space. So if you are doing the filtering in a spatial domain, so it is called as the spatial filtering. So spatial filtering term is the filtering operation that are performed directly on the pixel of the image. Whereas in frequency domain, what we do basically, we have to take the transform of spatial domain into the frequency domain by using either Fourier transform or like that. So you have to represent that image in a Fourier domain, and then after that you can apply the low pass filtering or high pass filtering or whatever you need, and so on. So that is called as the frequency domains filtering. Here we are going to talk about only the spatial domain filtering and so on. So but before that one, let me clear that what is meant by the spatial frequency in the image. So spatial frequency in the image is called as a it is the rate of change of pixel intensity. It is defined as a rate of change of pixel intensity. Now see that, for example, this image is 4x4 image, means 4 rows are there and 4 columns are there. So total number of pixels are 4x4, that is 4 into 4 equal to 16 pixels are there. Now all pixels are having intensity equal to 0. So what is the rate of change of pixel intensity? Now see, suppose for example, if I'd like to display this image on a computer screen, it will be just black image because 0 is considered as a black and 250 pi is considered as a white, this one. And between 0 to 250 pi there are various gray shades and so on. So when you represent this image on a or display this image on a computer screen, it will look like as a black image. Now see, what is the spatial frequency of this image? So rate of change of pixel intensity, that is nothing but the difference between the two consecutive pixels. So what is the difference between two consecutive pixels? That is 0 minus 0, that is 0. Again, 0 minus 0, it is 0. 0 minus 0. So wherever you go, you will find the rate of change of pixel intensity is 0. And that's why this image is considered as a low spatial frequency image, right? Now, low spatial frequency image, what we can conclude from this one is that all those neighboring pixels are having the same intensity. Then that part of the image is called the low spatial frequency of the image, and so on. Similarly, look at this one, second image. Now here, all the pixels are having intensity equal to 250 pi. So that is the maximum intensity in grayscale. So when you visualize this image on a computer screen, it will look like as a white image. Okay. Earlier image, it was a black image because intensity was 0. Now, what is the spatial frequency of this image? Again, the rate of change of pixel intensity. See, 250 pi minus 250 pi is 0. Again, this 250 pi minus 250 pi is 0. 250 pi minus 250 pi is 0. Wherever you go, whether you do scanning from left to right or top to bottom, you will find the rate of change of pixel intensity is 0. So this image is also a low spatial frequency image, right? So it is a low spatial frequency image. This is also a low spatial frequency image. Okay, so you know that means basically when we can say that image is considered as a low spatial frequency if their neighboring pixels are having same intensity. Now, whether suppose for example I have an image like entire images of 128, 128, 128, so it will look like as a grayscale gray image. But if all the pixels are having same intensity, so rate of change of pixel intensity will be 0 in that case. So that is also considered as a low spatial frequency image. Now consider this image. Okay, so this row is basically 0. This is 250 pi. This is 0, having intensity equal to 0. The fourth row is having intensity equal to 250 pi. Now, when I display this image on a computer screen, it will look like as this as a black band horizontal line, and then because of this 250 pi, it will look like as a this one white line, then again this is a black line, and so on. So basically we can see that these are the horizontal edge image and so on. So when I basically scan this image from left to right, and when I find the spatial frequency between this one, 0 minus 0, it will be 0, and so on. So for second row also it will be 0, and so on. But when I come from scanning like 250 pi vertical scanning, so 250 pi minus 0 will be 250 pi. Now see that between this one and this one, rate of change of pixels intensity is high. Now when you go from this black to white, there is an edge. So what we can conclude, see that same thing happens, like okay, from 0 to 0 minus 250 pi will be equal to minus 250 pi. So when you are going from black to white to black, again there is an edge, or black to white, again there is an edge, and so on. So when the see when you are crossing from one intensity to the other intensity, you will find there is an edge. So edge contains high spatial frequency component. See that this is a high spatial frequency component. When you are changing from this to this, you come across the edge. So edges in the image are considered as the high spatial frequency component. Now consider the fourth image. Like for example, instead of this horizontal, I have considered all those pixels, vertical pixels are having 0, then 250 pi, 0, 250 pi, and so on. When I display this image, fourth image, it will look like as a this one, black vertical line, then white vertical line, then black vertical line, and then white vertical line, and so on. So now when I go from scanning from, or when I find the rate of change of pixel intensity, and when I'm scanning from left to right, so 250 pi minus 0 will get the high value of spatial frequency, that is 250 pi, and so on. Now see that means here again, when I'm scanning from left to right, so I come across the edge, and edge is nothing in the image. Edge is nothing but the high spatial frequency component. So the intensities where okay, all neighboring pixels are the same intensity, that area is considered as a low spatial frequency area. But the area where there is a edge, at that time rate of change of pixel intensity is larger, whether you consider the vertical or horizontal. Also rate of change of pixel intensity at the edge border is larger, and that's why edges in the image are considered as a high spatial frequency component, right? Similarly, what is my noise basically? Now see that I have the image like as a this one 4x4 image is there, 4 rows and 4 columns are there, and most of the pixels are having intensity equal to 0. So only one pixel is there having intensity equal to this one is 250 pi. So that is maximum intensity. So you will when you display the image, you will see that there is a background, and then there is one white spot. So this white spot is considered as a basically noise in the image. And then what is the frequency of this noise? So if you basically find the rate of change of pixel intensity, see 250 pi minus 0 is 250 pi, or 0 minus 250 pi is 0, or 250 pi minus 0 in this direction is also 250 pi, or 0 minus 250 pi is also maximum. So at noise this one location, rate of change of pixel intensity is high, so noise is considered as a high spatial frequency component in the image. All right, now you know that when you have to remove the noise, means basically you have to remove the high frequency component. So definitely you have to use the low spatial frequency filter. So that is low pass filter, that is nothing but the averaging filter, or this one median filter, which is generally also a nonlinear filter. We'll see what is my linear and nonlinear filter, and so on. right? So for removing the noise, you really need a averaging filter, or basically low pass filter, and so on. So I hope that you got the idea about what is the noise in the image and so on. Now see how filtering is done. Okay, so you know that original image is there and you have the filter mask, and this filter mask is basically rotated or moved on this one, applied on this image, and then you get the filtered image. So or basically image is filtered by using filter this mask. Okay, so this is your input image, and these are the pixel values of the image. So all those are the pixel values, and these are nothing but the weightage of the mask. So this mask is nothing but it is called as the filter, or this is also called as the sum image. Sometimes it is called as the window, sometimes it is called as the kernel function or template, and so on. So there are several terms basically generally people use alternatively for this one. So what do we do? Basically we pass this image, or basically we move this mask from left to right, and then from top to bottom, and then when you do this operation, that is nothing but the convolution operation, you get the resultant image, that is nothing but the filtered image. Now when you get the filtered image, basically these pixels will not remain as a pixel, but these are called as the coefficients of the filtered image. So you have this input image, this is the filter mask, and when you are applying this filter mask on this image, you get the resultant as the filtered image. So in the input image you have all those pixel values. So these are not called as a pixels after filtering, those are called as a coefficients in the image. So image is filtered by doing what? Convolution operation. So this convolution operation with other sub image. So this sub image is nothing but the filter mask, or sometimes it is called as the kernel, or sometimes it is called as the template, or sometimes it is called as the window. So kernel, mask, template, window is a set of weights. So these are the separate of weights. So for low pass filter, this will be having different set of weights. For high pass filter, it will be having different set of filters, this one weights, and so on. And also the size of the mask also changes. Means here I have shown you, for example, 2x2 mask or 2x2 filter. You can have the 3x3 filter. So total number of weights will be equal to 3x3, that is equal to 9. Here 2x2 will be equal to 4, and so on. So or I can have generally a mask of like, for example, generally odd mask is considered as a 3x3 or 5x5 or 7x7, and so on. So this filtered image is nothing but the this one. The filtered image has the information that the mask is from the image,